Welcome to our exploration of asymptotic notation, where we'll learn about big O, omega, and theta notation, the fundamental tools for analyzing algorithm efficiency. Let's start by setting up our coordinate system. The x-axis represents input size n, while the y-axis shows the time complexity of our algorithms. First, let's understand big O notation, which describes the upper bound of an algorithm's time complexity. It tells us the worst-case scenario for how our algorithm will perform. Here we see a quadratic function in blue, bounded above by another quadratic function in red. The mathematical definition states that f of n is less than or equal to c times g of n. Now let's move on to omega notation, which represents the lower bound of algorithm complexity. Omega notation describes the best-case performance of an algorithm. It establishes that our function f of n will always be greater than or equal to c times g of n. The orange curve shows the lower bound. Our algorithm will never perform better than this threshold. Finally, we have theta notation, which gives us the most precise description by providing both upper and lower bounds. Theta notation combines both bounds, showing that our function is squeezed between two boundaries. This gives us the tightest possible characterization of an algorithm's growth rate. We can see both the upper and lower bounds surrounding our function, creating a bounded region. This purple shaded region represents where our function must lie when we have theta bounds. It cannot escape this bounded area. Now let's explore the most common time complexities you'll encounter in computer science. Here are the 6 most important complexity classes, ranging from constant time, which is the fastest, all the way to exponential time, which grows extremely rapidly. Constant time operations take the same time regardless of input size. Logarithmic grows slowly, linear grows proportionally. Linearithmic is common in efficient sorting algorithms. Quadratic involves nested loops, and exponential grows explosively and should be avoided when possible. Let's visualize how dramatically these different complexities grow as input size increases. Notice how the exponential function shoots up rapidly while constant time remains flat. Understanding these growth rates is crucial for writing efficient algorithms. Always strive for the lowest complexity possible, as the difference becomes dramatic with large inputs.